with AI services and solutions for molecular modeling and design using quantum and high performance computing. He's also founder and CEO of Quantalane and Alain Chance business management consulting startups. Alan is also the co-author of the book Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit, which was published in 2020. Alan is also a Qiskit advocate and an IBM certified associate developer. He has completed several quantum hackathon and challenges since 2018. He has over 30 years of experience in major enterprise transformation projects with a focus on data management, governance, gained in major management consulting firms. He has a diploma in mining, civil engineering from School of Mines of Saint-Étienne in France, 1981. And without further ado, I'll pass it on to Alan.
Oh, thank you, Payman.
Welcome.
Actually, there was a typo. My book came out in May of 2022. But I will now share my presentation. So let me see if I can do that. Just bear with me.
Yeah. Sure.
Let me hold on. Just a second. Hopefully you can see my screen. I will make it bigger.
Yeah, we can see your screen.
Okay, so hold on. There we are. Just bear with me, trying to make it bigger. So, okay, yeah, there we are. Hopefully, can you see my presentation? Big screen, excellent.
Yeah,
so
everything's set.
Thank you so much for inviting me. It's really a privilege to be a speaker at your World Quantum event. So this is the agenda. So I will make an overview of the latest trends in quantum chemistry. Then there will be an interview of my me as a co-author of my book, and last but not least, we'll have questions and answers. So I will ask all the participants to be patient, and if they have questions, please, we will have a spare time at the end. Okay, so with no further delay, let's start. So this is me. So challenges and opportunities. So first of all, what are we talking about? So there is not just quantum chemistry, which is basically the quantum mechanical treatments of electrons. And basically quantum chemistry has been there for quite a while and doesn't require quantum computing. So quantum chemistry doesn't imply we are using quantum computing. There is quantum molecular dynamics, which goes beyond the treatments of electrons. It's both electrons and nuclei. And there is also the molecular dynamics, which is the classical mechanical treatments of nuclei. Okay. So let's move on. So the main challenge has been for so many years and still is nowadays to balance accuracy versus speed of computation. In quantum chemistry, accuracy is absolutely essential. The chemical accuracy must be reached, or otherwise the simulation have little or no value. So the thing is, as we shall see, we have methods for simulating chemical reactions with exact quantum molecular dynamics methods. However, in practice, because the computational complexity scales exponentially with the number of particles, electrons and nuclei, that in practice, it exceeds the capabilities of supercomputers. And so it's the reason why for many years, since the 1960s, methods have been developed using approximations, and the best known of them is the so-called Born-Oppenheimer BO approximation, which assumes that the motions of nuclei can be uncoupled from the motions of the electrons. And the Born-Oppenheimer approximation works really fine for a majority of cases. However, it does fail, and sometimes dramatically, like in the example mentioned at the bottom of this page, to simulate certain molecular dynamics systems. For instance, when hydrogen atoms collide with semiconductor surfaces. This is a very recent paper. So the challenge is actually not just the computational complexity, which scales exponentially. It's worse than that. Sometimes we don't even have the right model to simulate nature. Okay. So what can we do about that? Well, the good news, artificial intelligence comes to the rescue. Top experts hold the view that AI will help solve the theoretical challenge by introducing generic models for quantum chemistry. So some of the best experts call that chemistry 2.0. And there are good reasons to believe that within the next 10 years, in terms of theory of chemistry, there will be something really much different, chemistry 2.0. Okay. Now, a good example of that is, and again, this is a very recent paper, ChemCro, like chemistry, like how it's the use of GPT-4 to apply to quantum chemistry, and the idea is that it would definitely help expert chemists and lower the barriers for non-experts. However, the cautions we must be extremely cautious when using such tools. It doesn't mean that, especially if non-experts use it, because we must have knowledge to determine that the answers are actually relevant. So this is well explained in this paper. Okay, augmenting large language models with chemistry tools. But this is very promising. Now, another often overlooked opportunity with quantum chemistry is to design so-called molecular qubits. And it's something which is still emerging. We don't know yet at this stage whether molecular qubits will manage to effectively design and build such molecular qubits, but it's worth exploring. And it's not as advanced as other types of qubits, like superconducting loops or ion-based qubits. But nevertheless, this is really interesting. And there has been some demonstration that we can shield molecular qubits that respond to light against noise, because this is one of the main challenges with qubits, is to shield them from noise. And this can be achieved very elegantly with by chemically controlling the molecular environment. So this is still early age, but it opens the door to applications like in nanoscale sensing of electric fields. So it's not just quantum computing. Those qubits could be used also for sensing. Okay, So there was a post I made last year. I invite the participant to have a look, and of course I would share this presentation. Okay. Now let's move on to hybrid quantum classical algorithms. In reality, there is no such thing as a pure quantum algorithms. All the algorithms, quantum algorithms I've read about, heard about, are actually hybrid when you think about it. So I've selected the 3 very recent papers which illustrate these algorithms. So the VQE stands for Variational Quantum Eigensolver. So I won't explain it in details. It's explained in chapter 5 of my book. And DFT, density functional theory. DFT is a well-known classical approach. The point here is these authors have put forward a method which combines the variational quantum eigensolver algorithm, which is very popular in the quantum computing arena, not just for quantum chemistry, with the density functional theory method. So it's illustrated on the right. This is a very promising approach, and there is a very good paper, but it's for simulating systems with strongly correlated fragments of molecular systems on a quantum computer. So that's the first thing to notice. These promising methods, each one of them has a particular domain of application. Okay. Now the second example, again, very recent paper. First of all, there is a new open source quantum computing package, which is called OpenVQE. So it's MIT licensed, so it can be used freely. And so it's yet another welcomed open source quantum computing package for chemistry. And it is based on the very popular unitary coupled cluster method, classical method. And again, it leverages the variational quantum eigensolver extension. So it's of the quantum learning machine. Quantum learning machine, not to be confused with quantum machine learning, is an offering from Atos to simulate quantum processors up to something like 40 qubits. Okay. And the first application of this OpenVQE quantum computing package is a new method which has been called UCC-SDT, which stands for Unitary Coupled Cluster, Single, Double, and Triple Excitations. For those interested who are not familiar with this, again, in chapter 5 of my book, it is explained. But the important thing to notice there is that this method is focused only on neutral closed shell molecule species, which means that the electrons are paired. Okay, and so they have achieved very interesting results because the accuracy is improved by using triple excitation as opposed to the as compared to the popular UCCSD, which only uses single and double excitations. And then the authors have very cleverly exploited both spin and orbital symmetries to reduce, and this is really essential, to reduce the quantum circuit depth, the number of gates which is required to implement these algorithms, but at the same time reach chemical accuracy. So this is a very, very promising, well-balanced approach for achieving chemical accuracy while reducing the circuit depth. However, as pointed out in the paper, in order to to use chemical basis sets beyond the most basic one, which is STO3G, and again, this is explained in my book, we still need to wait for quantum processors which have better capabilities in terms of the the coherence, so that we can run circuits with many more gates than currently. Currently, I would say that most quantum processors, they can run up to, say, 100 gates before they decohere, which is great for experimenting, but it's far from enough for running circuits, quantum circuits that would be of practical value for quantum chemistry. The order of magnitudes for quantum chemistry is several 100,000 gates. So we are several orders of magnitude away yet, 2 or 3 orders of magnitude away from. But nevertheless, this is a very promising method. And the last one, which is beautifully illustrated on the left-hand side, shows the way it works. At the moment, the best we can achieve is to hand over to the quantum computer the measurement of a bunch of circuits, which make it possible to get the expectation value. And the bulk of the algorithm is actually run on a classical computer. So at the moment, the researchers are trying to see how to properly split the work between what is achieved on the classical side, which is quite a lot actually, including the gradient descent of optimizing the so-called variational quantum circuit, which is simply a quantum circuit which is parameterized and which makes it possible to determine expectation value, hence the typically the ground state energy of a molecule. And the optimization, the gradient descent, is performed on the classical computer. Okay, so these examples, very recent, give an idea of the current state of the art. I will take questions at the end. Okay. So now let's focus on artificial intelligence and quantum computing. So we live at a time when the hardware is really working hand in hand with the algorithms. We've just seen hybrid classical quantum algorithms. And the good news is now we have tightly integrated quantum classical computing platforms, which can boost artificial intelligence, which we have seen before is very promising for chemistry 2.0. And of course, hybrid quantum classical algorithms, which are applied to quantum chemistry. So let's have a look. So NVIDIA, a couple of weeks ago, announced their so-called CUDA quantum platform, which is a hybrid platform, which is designed from the start to tightly integrate the NVIDIA graphical processing unit, GPU, which are very well used in high performance computing, supercomputers, and the new quantum processing units. And the illustration on the right shows that it's really well suited to support those hybrid algorithms. So the expectation value is typically performed at the QPU, the quantum processing unit. And the factorization, here the LU, which stands for lower upper factorization, which is essential to determine the eigenvalues and then typically the energy, the ground state energy of a molecule or an atom. It's still performed on the classical side. We are still a long way before we can use pure quantum algorithm like HHL, HHL to perform such things. So the heavy lifting in terms of factorization is still performed, but it benefits then from the graphical processing unit. Okay. Another very interesting example is Qiskit Runtime, which has been made available at least for a year now, but it's very recent. So it's both a quantum computing service, and it's also a programming model. And Qiskit is an open source framework, which is sponsored by IBM, but it's open source. And Qiskit Runtime optimizes the workloads by introducing two primitives, estimator and sampler. And the bottom line, it reduces the number of jobs, because it means a number of iterations, typically for variational quantum eigensolver, where there is an optimization loop. It's performed. You don't need to submit one job to have many iterations, and it really it boosts the performance. And one illustration is actually in a field which has nothing to do with quantum chemistry, but quantum cryptography. In May, I will present, will be a speaker at an event where I will show a very interesting application of Qiskit Runtime for the quantum permutation pad. An improvement in performance, absolutely amazing. And again, this architecture will benefit from tightly integrated hardware, which integrates the new quantum processor units with high-performing mainframes, or even better, supercomputers. Okay. So we Taha Selim, who is next to me, and myself, we have a vision that researchers need much help to choose the right algorithm depending on the problem they are trying to solve, and also the right platform, the right integrated platform to effectively perform their work. So we are co-founding Molket, and it is based in the startup village Amsterdam, where I'm sitting now, from which I'm presenting this deck of slides. And it's a vibrant community of startups and academic partners. And their focus is not just on quantum computing, but it's also artificial intelligence. So you see, nowadays we should think of not just quantum computing in isolation, but AI and quantum computing working hand in hand and synergistically helping one another. Okay, so the vision is we will provide a cloud which will assist researchers in determining the best combination of algorithms and platforms, and potentially also to run benchmarks to determine which is the best combination in a pre-selected set of algorithms and platforms. And so, the idea also is to leverage artificial intelligence to do that. So artificial intelligence at several levels. Okay. So, and where I'm sitting, we had the privilege of having a state visit by the President Emmanuel Macron of France, together with His Majesty the King Willem Alexander of the Kingdom of Netherlands. They both visited the Quantum Gases and Quantum Information Lab at Amsterdam Science Park. And this was this week on the 12th of April, and I've put the link down there. So we are really lucky, I would say, to have this political willingness to make things move in this emerging field of quantum computing, and in particular quantum chemistry and AI. Okay, so for those interested, I give a bunch of references. It's only a selection, but these are fairly recent references. So you will have good reading, because these references, a bunch of them are very, very recent. Okay. And AI and quantum computing. Okay. So I think that's it for my presentation. I guess we're fine with time. So next in the agenda, welcome my interview as co-author of my book. I prepared a few slides just to start the ball rolling. So basically, the purpose of my book, I would say, keepers in my book, is to help a large audience, and especially students, even from high school, to acquire knowledge of quantum chemistry concepts, starting with the postulates of quantum mechanics, the foundation of quantum computing. But what is really exciting is to execute illustrations, which I made with Python code and Qiskit, which is an open source quantum chemistry package. And now, beyond the marketing of the book, we, the lead author, Dr. Kipper Sharkey, Pact Publishing, we collaborate on marketing our book to kids in high school and middle school. And we are discussing with several communities, sponsors and mentors of quantum chemistry and quantum computing learning programs. And I've been told that Q Iran has a study group about our book. So from now, I don't know who, Payman, who would like to interview me and ask questions about. Yep.
Omid will do the interview, I suppose. Omid, would you please take over?
Okay, thanks, Payman. Can you hear me, Payman?
Yeah, I got your voice clearly.
Okay, thanks, Alan, for your interesting talk, and thanks for presenting some recent paper. It was like 2022, 2023. It was very interesting for me. I should look at your presentation again after talk. And with this slide, you have already answered few general question. For example, I want to ask you, what audience did you have in your mind that you mentioned that, yeah, from high school even to more undergrad?
Actually, I was invited by Dr. Alain Chance, who is the lead author, to illustrate a book, and she was asked to publish the book since 2020, but because of COVID, that was delayed. But from the very beginning, the intent was to make it accessible to an audience, typically potentially quantum chemists who are really expert in their field, but hear about quantum computing and they are curious and would like to know how it's going. But the converse also, and I'm a good example of that. The people who took part in hackathons, quantum challenges, and got their hand dirty playing with Qiskit nature, but they didn't have the proper education in quantum chemistry. So that's the typical audience, but also very young students. And we have been in touch, Keeper and I, with students aged 15. Some of them took the initiative to set up like a club with their comrades, and together with the sponsorship of their teacher, start self-teaching themselves the basic of quantum mechanics. But the big difference with my time back in the 1980s, when I was taught quantum physics, was the mentality: shut up and calculate. I mean, don't try to understand, just work. Nowadays, with programming, it's a completely different. So from the very beginning, we had in mind middle school students, and but also professionals, quantum chemists, quantum computing enthusiasts. Okay.
Yeah. I also have some chemist friends, and they want to start the quantum computing journey and ask me a preference book. I usually recommend your book because when it comes to books in quantum computing. When you search, you can see a lot of books, but I haven't seen the similar book like your book, Quantum Chemistry Application of the Quantum Computing. I want to ask you about this topic. Do you have any similar book like your book or not? Because I haven't seen personally.
So that's a very good point. Thank you. I'm grateful for your comment, because honestly, we believe that we fill a gap, because there are so many outstanding tutorials for the people who want to get started about quantum computing. There are many high quality books available, but usually they spend so much time explaining the basics that you get up to a certain point, okay, which is great. And then of course you can practice with hackathons and you know, those I've attended all the quantum challenges organized by IBM since 2020, but there are other, okay. And it's really great also from a social standpoint, because you're not on your own, and you can learn from people who have got more experience than you. But typically then you get familiar with kind of package, which makes it apparently easy to get results, but it's frustrating because you know, when you take part in those hackathons, they explain, hey, you see, this is the Hamiltonian, this is, and then that's it. Okay, and then if you want to get acquainted with the quantum chemistry, you can look white papers and papers, but then it's really tough. The gap between the state where you are when you have read all those great tutorials and the quantum chemistry is huge, and I think our book fills this gap. And especially also the idea of experimenting, because along with the book comes a set of Jupyter notebooks. And I'm basically the one who wrote most of these Jupyter notebooks, which makes it possible. It's like an executable version of the book. You cannot, of course, you can just read the book, okay, but better you can get hold of the Jupyter notebooks, and every purchaser of our book is entitled to get for free a set of complete Jupyter notebooks, which contain the book and more, actually. So the text, the images, and the code, and you can rerun the experiment, and you can change the parameters, okay, and that makes the experience completely different. So yes, I think the book is yeah, it fills a gap, and it's different from the others as far as I know. Yeah.
Actually, my next question was kind of about the hands-on which come with your book and your Jupyter notebook. That was, you know, when it comes to quantum computing, when it comes to programming, I think the hands-on is a kind of inevitable part of a book, because you cannot just read some code, and you need to implement, you need to program by yourself. And thanks to your book, I know in your GitHub page, I think people can find many examples of.
So on the GitHub page, it's only the so-called cut down version. So it's only the code. Those who purchase the book, in the preface there is a QR code, and there is a website. Okay. So when you have purchased the book, then you're entitled to have a more complete version of the Jupyter notebooks. There are two versions. There is the public one, which is on GitHub. You can grab it for free. It's free. Okay. But then, of course, you don't have the explanations. So it's like a teaser. Hey, there is the code. But if you want, you know, you've got to buy the book. Okay. And when you buy the book, you got the complete set of Jupyter notebooks, which is basically you can put the book aside, because you have got everything in Jupyter notebooks. And actually, because we use LaTeX, the quality of the text, the mathematical derivations, it's actually very impressive. Yeah. So.
Sorry, Pemo?
It wasn't me, I guess.
Okay, Ali. Okay.
Okay.
Thank you. Okay, thanks for your clarification, and that's good to know. And I want to ask you a little kind of technical question. Can you briefly explain I know that you cover Qiskit nature in your book. I'm curious to know the connection between the Qiskit as a quantum package or quantum CK with the classical part software package, like Cipher or PySCF.
Okay.
And it would be great to briefly explain this part.
Now, this is really important because it's something I discovered by practicing, especially because once I had this idea of running a simple, I call that an experiment, with the Qiskit nature and the competitor, Google Open Fermion, and I got different results. And say, well, where does it come from? And I realized that actually those packages, they are piggybacked on PySCF. So actually, and this is fine, but it's not obvious at first that the bulk of the work is performed by a classical, very good package, which is by Python SCF, and Qiskit nature brings added value, obviously, but the key, and it's well explained also in my book, is to properly balance what is handed over to PySCF, what is handed over to the added layer, Qiskit nature. But as I've shown in my book, there are other packages beside PySCF, like Cipher, for example, which are very, very effective, and also popular packages like PyQMC. QMC stands for Quantum Monte Carlo, which are very competitive against VQE because they are classical approaches which are variational as well. And I think it's good to not just to focus on a package like Qiskit nature, but also to have a broader view. And again, this is the advantage of reading my book, is that it will give you, and then people can make up their own mind about where we are today and where we hope to be. And also, I think it's good practice. So say someone uses some of this package like Qiskit nature, they should have the reflex of checking the results by using some other classical package. At least for now and in the foreseeable future, we will be able to run these computations using purely classical software, which is important. You cannot just rely on getting results from a package like Qiskit nature. You've got, because you could run outside of the scope of proper usage of the to-do. So yeah, it's very important. So the relationship is very intimate. Qiskit nature would not work without PySCF, and I think it's the same with Google Open Fermion.
Okay. And do we need a special operating system like Linux or Ubuntu or something, or we can run your example in Windows as well?
So when I wrote the first version of the book, I did test, as I mentioned in the book, in both the IBM Quantum Lab environment, which is free. You just need to get to login, and also Google Colab, which is very convenient for collaborating with my lead author, Dr. Kippel and Sharkey. But in, I think it was last year, for some reason, the version of Python, which is supported natively by Google Colab, at least the free version, was not adequate to run Qiskit nature. Yeah, that is one thing. But the thing in which my notebooks, the Jupyter notebooks, which come along with the book, they can be run locally. This is what I do most of the time in a distribution of Linux. The one I use is Ubuntu, and that runs under Windows very neatly. So yeah, it's very simple to install the environment, including Qiskit nature, in Ubuntu, and it can be run either natively or under Windows. And this is what I do, and it works really well.
Both operating system works very well.
Yeah, I mean, Ubuntu under Windows has been integrated a couple of years ago, and now it's really neat because you have the advantage of both worlds, right? You can run your Jupyter notebooks, you know, it's just like in your favorite browser. You're just one you know, one window, and then but actually it runs under Ubuntu under Windows. That's my experience. So Taha, my co-founder, has got a different environment, and he uses thank you. What do you use? You use
Mac OS.
Oh yeah, as you use Mac. Okay, I'm not familiar with Mac, so but it does work. So you have the choice. I mean, the readers can choose a platform. Definitely, IBM Quantum Lab would. I mean, that definitely will work because Qiskit is sponsored by IBM. That's for sure. But also, yeah, under Ubuntu, under Windows and other environments. Yeah, and also pure Linux. Yeah.
And okay, I just want to ask, this is actually my last question, but it's not related directly to your book. It's related to the your startup. As you remember, we both participated in Strasbourg in
Yes.
quantum chemistry, yeah, in
Yes.
France. And that actually workshop, and the Japanese startup Kunasis show the platforms. And in what aspects do you think your platform is different from the similar one like Kunasis or the other similar platforms?
Oh, that's a very good question. Maybe I will invite my
Why not?
co-founder to comment as well. But I think a key difference. We're not just aiming for education, but also to provide a service as a superposition of both. We are a superposition of both a tech company, but also a service-oriented company, and starting with the idea of assisting people in researchers, but not just researchers, employees in companies that could be pharmaceutical companies, could be personal care companies, to solve real problems. And we start from that end. And it complements other startups which are pushing their solutions and looking for problems to solve, right? And so the difference being, I think, we complement. I mean, we complement companies like Unisys, but I think our target is the difference also is offering a cloud which will with AI and partnering with entities, especially those in the Startup Village Amsterdam, which provide hardware, and those based in Delft, which is another innovation center in the Netherlands, which provides hardware. So, but I think this is a topic we would like to discuss further together with my co-founder. Thank you for asking, Omid. Yeah.
Yeah.
Okay.
Excuse me. Mustafa.
Yes. Hello, Omid. How are you?
Hi.
I have a question. Can I ask?
Yes,
Yeah.
please.
Yeah.
I think now is the time for the questions and answers, I think.
Hi, Alain. Thank you for accepting our invitation for presentation. Thank you. And I have a question. As we know, we use a density functional theory approach, and we use in our classical system to calculate electronic structure of material, but in ground state. If we have another version of a density functional theory, we call it time dependent, or TDDFT. Time dependent, we use for calculating a kind of excitation in our system. For example, optical transition and something like that we use to calculate optical properties of the material at nanoscale. I would like to know if any kind of implementation VQE algorithm, variational quantum eigensolver, with the time-dependent version of DFT is any kind of method to implement both of them, because DFT is in a kind of static mode, but we have a kind of dynamic mode. For example, we have a kind of transitions between the bands in band structures. For example, we want to calculate this kind of properties in our material. I would like to know if we have any kind of implementation VQE with time-dependent version of DFT. Thank you.
Okay, thank you. Very good question. The honest answer is right now, I don't know, but we will look it up, Tara and I, because it makes sense, yes, to see whether there is any. It makes perfect sense to me to combine VQE with your time-dependent approach, definitely. Again, it illustrates the challenge for us, I would say, as a community, to determine what is out there. There might be gems developed by some universities somewhere around the world that only a few researchers are aware of, and we must spend time and effort to search for those, whether this has been already implemented or whether it's a brand new idea. And the honest answer right now is we don't know, but it's a very good question. It's worth exploring. And this is the idea also with Molket, to make it easier in the future to have, like I would say a living knowledge base, so that we could say yes, indeed, and even better, we have integrated this solution in the ecosystem of the cloud, which we will offer. So thank you for asking. Unfortunately, no, I don't know.
Thank you for your great presentation.
All right, thank you, Alan and Amit, for the interview. If you have any questions, you can either directly ask and unmute yourself, or just write to us and we will address those questions. All right.
Don't be shy. No, there's no silly question.
Yeah.
Sorry,
I can
maybe after this event, how can people reach out to you, Alan?
Oh, very simply. LinkedIn is a good way to get in touch with us.
I know.
But otherwise, we put. I think in the slides we put. We put at the bottom addresses by email. So but yeah, I mean, both Taha and I can be reached on LinkedIn, but also directly for general inquiries down there. I think hopefully you can use LinkedIn and access us.
Yeah, I actually can ask a question. I saw that you announced like Quantum Chemistry 2 is coming out. So how would you elaborate more on that? Is it the volume 2 of the current book? Are you going to cover more advanced topics, or what is it about?
Well, so let me go back to the slides. So I refer to the opinion put forward by Matthias Bickelhoopt, who is a professor of theoretical chemistry at the Vrije University Amsterdam. What's interesting is that this addresses one of the challenges So most people think, okay, the challenge is in quantum chemistry is balancing accuracy versus speed, which is true. But there is this other big challenge, is that some of the very effective approximations, like Born-Oppenheimer, because they fail miserably, we need to find something better. And this is very exciting. And AI has the potential to be trained on mechanisms. So, for example, the different binding mechanisms, what the different binding mechanisms are. So we, Taha and I, we believe that AI would help solving the theoretical challenge by introducing generic models for quantum chemistry. So this is something very exciting, which complements the other effort, which must be run in parallel, just to try and optimize, to better balance accuracy versus speed. It's very interesting, and this is the reference at the bottom. This is a very recent paper that's such a simple experiment, making hydrogen atoms, which are the simplest atom, right? Hydrogen atom collide with semiconductor surfaces. And the experiment shows that the prediction based on the Born-Oppenheimer approximation, they fell dramatically. And this is really exciting for those participants who are researchers. If they want a topic where they could shine, I mean, just, this is it. This is an experiment which falsifies the, or makes the, puts to shame the Born-Oppenheimer approximation. Okay, so this is something, and we believe artificial intelligence could help put together these new models. I think that's my answer.
Thank you. And let me ask you another question. So consider that I'm an electrical engineer, and I want to enter quantum chemistry. Is there any fundamental knowledge, like in physical chemistry, or I don't know, inorganic chemistry? How much chemistry is needed to enter this field and become a researcher? I guess that would be very important for many of us.
Yeah. What's interesting is I'm not myself a researcher. My professional career has been more consulting, but this is I'm grateful you asked this question, because honestly, what I believe is the following, and this is good news for everybody. People should feel comfortable that getting a PhD is like a proof of intellectual agility. Which means that and a method of working, a method of solving problems. This is what matters to employers, and this is what makes the knowledge gain, because the knowledge, you know, after a couple of years might become somehow obsolete. However, the experience gain during as a researcher solving problem can be transposed to others. So I think, and the other important thing is, and it's often overlooked, the value of a degree, of a university degree, is also the network of alumni, the network of people who have a degree from the same university. This is really important. So I would say the good news is that there are so many different career paths possible. I think it's essential to master linear algebra in mathematics. What else? Ideally, to be taught the classical, well-known theories, DFT, density functional theory, the coupled cluster, because they are still used as a basis, combined with new ideas, but also at the same time to be agile enough to put aside this knowledge and be able to think outside of the box. I think one of the, and it is really important, not to be too specialized, too expert in one field, because that might make it more difficult to be agile enough to think outside of the box. I think nowadays what has been attempted in quantum chemistry is to recast classical methods into a quantum computing framework. Okay, it was worth trying, but we see that, you know, it's still quite a long way. I mean, when you read my book or other papers, you realize that mapping classical quantum chemistry approaches, which work really well, into the quantum computing framework means we end up with requirements of running quantum circuits with hundreds of thousands of gates, which puts the target for those who try hard to build those quantum computers very far away. Whereas maybe there are completely different ways, even innovative ways of approaching these quantum chemistry challenges that would make it possible to use next generation of quantum processors. So I think it's this is my view. And it's good because it means someone who, for example, would have been interested. There are examples, professionals who have been interested in astronomy, for example, started to learn about, you know, the physics of, I don't know, neutron stars and the like, and then redirected to quantum computing. And conversely, there are very good examples of a former prime minister in Germany who studied, was a quantum chemist, Angela Merkel, and ended up being a prime minister of Germany. And so, yeah, I think it's, you know, it's the education, the ability to solve problem, the network. This is really what matters more than the content of a particular cursus. Okay.
Yeah, thank you so much. So if there's any other questions, we would welcome to address them, but I don't see anything on a chat box.
Okay, so I want to thank all of those who participated, all of the organizers. It was really, I'm grateful you gave me this opportunity, and hopefully this will encourage students and other enthusiasts to study this field, which is developing rapidly. And I think it's exciting time to be in a position to develop skills in that area and to make things move. And to, I mean, the future is to a large extent, it depends on what we are trying to achieve now. If we think things are impossible, then of course we will never make them possible. But if we try hard and make it happen, and thinking outside of the box and having diversity in the skills as well, I think it's a key success factor. Thank you so much for inviting me, and looking forward to receiving connect requests on LinkedIn, and I will try and we will try together with Tara to find an answer to the question, very good question that was asked earlier. Okay, thank you.
Thank you, Alan.
Yeah.
Thank you.
Goodbye.
All right, thank you so much. Have a great day.
Thank you.
All right, so our next presentation